Hello, this is the third part of a four-part series about pipelining a simplified MIPS risk processor. In this part, we're going to discuss control hazards. Remember that we talked about the reason for pipelining, which is to increase the processor performance by making better use of the processor components more of the time by overlapping the instruction execution. By splitting the processor into multiple stages, we can allow different instructions to execute in different stages of the processor at the same time. When the pipeline is full, one instruction will complete the final stage every cycle, and so the cycles per instruction, or CPI, will be 1 in the ideal case. We examine the performance of a pipeline processor using this multi-cycle pipeline diagram. Along the top, we have the clock cycle numbers, and along the side we have the instructions as they are fetched in the order in that they are fetched from the program. So in clock cycle 1, we fetch the first instruction of the program. In clock cycle 5, we're going to be fetching the 5th instruction of the program, and we will be filling up our pipeline so that the end of clock cycle 5 has the first instruction completing. The MIPS control path also needs to be pipelined, and so the control signals travel down the pipeline through the interstage buffers along with the data flow lines. So as each subsequent pipeline stage consumes some of the control signals that pass down the pipeline get successively fewer and fewer until the final stage where the final control signals are used. In order to deal with data hazards, we introduced forwarding. So forwarding, or value bypass, is needed to route data that exists in the pipeline to instructions later in the program that need that data when they've already read their register operands and they've read the wrong values. We talked about this in the previous video. So the forwarding unit needs the source operands of the executing instruction, so the instruction that's in the execute stage, and it needs the destination of the instructions that are in the memory stage and the write back stages, along with their control signals to determine whether they will write to the same register that the instruction in the execute stage needs to read from. If so, then we need to forward the values from the interstage buffers where they exist, either in the memory stage or in the mem write back stage buffers. Those values go to these multiplexers that feed into the ALU inputs, and the control signals come from the forwarding unit logic. In reality, only the signals read write and mem write need to be made to a 0, but in general, the hazard unit is going to send a 0 control signals down the pipeline because it's a little bit simpler. So the hazard unit introduces a stall by adding those 0 control signals in case it detects a load use hazard. Remember that a load use hazard needs to add a bubble in the pipeline in order to separate the load instruction from a subsequent consuming ALU operation by one processor cycle. So the IDEX memread signal is plucked off of the control line and sent to the hazard unit in the decode stage in order to determine if the instruction in the execute stage is a load instruction. If it is a load instruction, and it's going to write its destination to the RT field, and that RT field matches the RS or RT fields of the instruction that's in the decode stage, and that instruction in the decode stage is also a R format or an instruction that uses that value, then the hazard unit needs to stall that instruction for one cycle, and it does this by freezing the interstage buffer between IF and ID so that the instruction that is being fetched will be fetched again, and stalling or freezing the PC write so that the program counter does not get updated, so that we don't try to fetch the next instruction after that. And then to add the bubble to the pipeline, we have this zero valued control signal that's going to get pushed down the pipeline. So a control hazard is when the flow of instructions is not sequential. This occurs because of control flow instructions or because of exceptions. So unconditional branches, conditional branches. In MIPS, procedure call and return is implemented by unconditional jumps. So the jump and link for a function call and jump return for a function return. Jump register for the function return. And then exceptions, which we may discuss at a different time. To deal with control hazards, we can stall the processor until we can know the decision. We can move the decision point earlier in the pipeline so that we can reduce the number of stall cycles. We can delay our decision making, and we'll see what that means, or we can use prediction. Control hazards occur less often than data hazards because control flow instructions generally occur much less frequently than non-control or ALU and memory operations. Unfortunately, there's nothing that it works as well against control hazards as value bypass does for data hazards. So here is our pipeline with our branch and jump hardware, and we've got the jump being figured out in the decode stage there. The topmost component of the decode stage is that shift left 2 to finish calculating the jump target, which will be appended to the PC plus 4. And the jump signal is determined in the control logic in order to control the multiplexer that decides what goes into the program counter for the next fetched instruction. The branch instruction currently finishes in the mem stage, where we've got that AND gate that's going to combine the 0 signal from the ALU with the branch signal from the control logic. So that's going to happen in the memory stage. So because the jumps occur in the decode stage, when we decode the jump, we've already fetched or started fetching the next instruction in the program. Now, with an unconditional jump, that instruction is never going to be executed. So we can fix this problem by flushing or squashing that instruction. So we can squash the instruction that follows the jump, and then the instruction at the jump target will be fetched in the subsequent cycle, and we will have a single no-op in the pipeline for that squashed instruction, and we'll be wasting 1 cycle. So essentially every jump instruction will be taking 2 cycles to execute because of the overhead of the flush. We'll flush instructions by adding this if.flush signal in order to control a multiplexer that selects between the fetched instruction and a 0 valued instruction. So let's take a look at a picture of that on the next slide. We'll clarify the notion of flushing or squashing from stalling. So there's really 2 kinds of stalls. One is to insert a bubble in the pipeline or add a no-op instruction dynamically. This is done in order to delay the execution of an instruction so that it can wait for its dependencies to be completed. So the instruction that's earlier in the pipeline, which is later in the code, needs to wait for something that is producing a value that it needs. And we can do this by adding a no-op by inserting zeros in the control line of the pipeline register at the stage that we want to introduce the bubble, and by freezing or not allowing the interstage buffers before that register stage, before that pipeline stage, to allow those registers to not latch new values. And then the instructions later in the pipeline will progress normally down the pipeline. Flushing or squashing is when we take the instruction that's in the pipeline and we completely get rid of it. And the way we can do that is by replacing its either the instruction itself or its control signals by 0, and allowing the essentially not freezing the pipeline stage buffers so that that instruction goes away. So in the decode stage, we've got our jump instruction, and we need to add this multiplexer in order to be able to flush the instruction that's being fetched, and that'll be controlled by the if.flush signal. Now for branch instructions, a branch backward in time causes a hazard. So the branch is figured out in the memory stage. Actually, the load word and even the instruction, the third instruction and instruction 4 are all going to be fetched and start executing before we've figured out whether or not the branch should be taken or not taken. And this is going to cause a problem because if the branch is taken, then we don't want to execute the load word or the other two instructions there. So we can fix this. One way to fix it is to simply insert a bubble or to flush the affected instructions. So we can just squash the fetch stage and repeatedly essentially changing the next three instructions into no ops until we know whether or not to branch. Now this will affect the CPI. Now every branch instruction is going to take 4 cycles instead of 1 cycle to finish. 4 cycles because we'll have 3 overhead cycles for flushing the instructions that are fetched until we know the outcome of the branch. A better way to fix this is to move the branch decision earlier so that we can flush fewer instructions. So if we move the branch decision into the decode stage, we will only have to flush 1 instruction. So let's see how we can do that. We can move the branch instruction into the execute stage, have the decision in the execute stage. This means that we would have only 2 stall cycles for every branch. We would need to have the AND gate and a 2-to-1 multiplexer in the execute timing path now. By pushing those from memory into execute, we may extend the critical path of the execute stage. A second option is to push the branch decision all the way into the decode stage, and this can reduce the number of stall cycles to 1. If we do that, we need to have forwarding hardware in the decode stage in order to forward values for the branch comparison. So the branch decision may need to have register values forwarded to it in the decode stage. We can compute the branch target address in parallel with reading the register file. We'll have to do this for every instruction because we won't know whether or not it's a branch until after the control logic figures that out. But we can do this and just ignore the result for anything that's not a branch. We have to wait for the register file to be finished reading in order to do the branch comparison. So this can extend the critical path of the decode stage if the register read happens at the end of the cycle. If the register read happens in the first half of the cycle, then we have less of a problem, but then we have to deal with the data hazards from write back to decode stage. For deeper pipelines, if the branch decisions are not able to be pushed earlier in the pipeline, then you'll have more stall cycles in general. So let's look at this branch forwarding, data forwarding problem a little bit more. The forwarding of values that are in the write back stage to the decode stage is handled already by the split register write and register read. By writing in the first half of the clock cycle and reading in the second half, you can you don't need to forward the value from the write back stage to the decode stage. So in this example, the write back to the $1 register will be ready when the branch instruction reads it in the register file. If that $1 value is being written in the mem stage, then we may need to forward from the EX-MEM interstage buffers to the decode stage in order to send it a value. The logic to do this is here. So if we're decoding a branch instruction and the EX-MEM has a non-zero destination, and the destination of the EX-MEM buffer is equal to the source of the ID stage, then we need to set the forward signal. And if it's equal to the RS, we'll do forward C equals 1. If it's equal to the RT, we do forward D equals 1. And we're going to have these forward signals will be controlling two multiplexers, similar to how data forwarding is done for the ALU. When the instruction that's immediately before the branch instruction writes to its one of its source operands, we have to wait for one cycle, at least one cycle, for that operation to produce the value that's needed for the branch comparison. So in this example, add1 there is going to write its result to $1. The branch instruction needs the value $1 for its comparison. Well, when add1 is in the execute stage, $1's value is unknown. And so we have to wait until that add1 finishes before we can forward it to the ID stage. It's just like the load use hazards, where you can't forward a value from one pipeline stage to immediately preceding pipeline stage when it's needed. We have to insert one bubble in order to allow that forwarding to happen. And that's done in the usual way by the hazard unit asserting the flush signal onto the multiplexer that's injecting the instruction, and by driving the control lines to 0 rather for the instruction that needs it. So the forwarding unit in the decode stage is going to need to get the signals that it needs in order to control the two multiplexers. Those multiplexers are going to get the values off of the EXMEM interstage buffers, and the forward logic will select either the values forwarded from the EXMEM stage buffers or from reading the register file. And then the hazard unit needs to be able to stall the fetching, and it also needs to be able to insert bubbles into the pipeline. And the if.flush signal to control squashing the next instruction after the branch is needed in case a branch is taken. We'll flush only one instruction following the branch instruction for a taken branch. So let's look again at these data hazards for the branch instructions. When the branch instruction consumes the output of ALU operations that are more than one instruction before it, then we can forward from the execute or we can forward from the execute mem stage, or we can get the value from the register file from the mem writeback. You could also forward it if the register timing doesn't work out. When the immediately preceding instruction is an ALU instruction, or two instructions prior is a load instruction, then we need to have a single stall cycle introduced in order to wait for the values to be produced. So in this example, the load result in $1 will be written back to the register file if we wait for one stall cycle after that add instruction executes. So we're waiting one cycle for both the add and the load results to be ready. When a load instruction immediately precedes a branch instruction, then we need to wait for two stall cycles because the load value is not ready until the end of the mem stage. And so there's two stages that we have to wait between when the branch instruction needs that value in decode and when the value actually will be available at the end of mem. So we need two stall cycles, and then we can get the value of the load instruction for branching. Another approach to dealing with branches is called delayed branches. The idea is that the instruction following the branch instruction will always be executed. So the next sequential instruction in MIPS, that'll be at PC plus 4, will be executed after the branch instruction. You can think of it like the branch is effective after that instruction. The instruction in that location is called the branch delay slot. So the compiler is generally responsible for finding instructions to put in branch delay slots that are safe to use. So we'll look at 3 different options for the compiler to use in general to find safe instructions. So option A is take an instruction from before the branch and put it into the delay slot. So here we have add $1, $2, $3, and then a comparison on $2. Since the result of the add going into $1 is not a dependency with the branch condition, we can slide that add into the delay slot. And because none of the red operands, $2 and $3, are written to by the condition, this is safe to do. We're not changing the dependencies of the program at all, the data dependencies. So we can just slide that in there. For B, we have this add $1, $2, $3, but now the branch condition is comparing $1, which means there's a dependency between the add and the if statement. So we can't move that add to after the if statement because that would change or alter the outcome of the branch condition. Something else we might be able to do is move an instruction from the branch target into the delay slot. So here we're thinking about maybe this is a branch backward. Then we can slide that sub instruction into the branch slot. This works as long as the sub instruction is going to be executed regardless of the branch, the leading up into the branch, I guess you would say. The problem is that the sub instruction may be executed from other targets that may not be related to the branch instruction, and so we might need to actually copy the instruction, the sub instruction, rather than move it entirely. Another approach is to pull an instruction from the fall through code. So if this sub instruction is independent of the code in the conditional block, then we can move that sub instruction into the delay slot as long as when the branch is not taken, there's no code in between there that modifies $4, $5, or $6. In general, the best choice is to pluck an instruction from immediately before the branch. In the other 2 choices, we may need to copy the instruction instead, which will increase the code size. And it has to be safe to execute that sub instruction regardless of the branch outcome. As pipelines get deeper and you can't push the branch decision point earlier in the pipeline, then the number of instructions that you need to find to fill up the delayed branch grows. So if your branch decision point is in your 3rd pipeline stage instead of your 2nd, then you need 2 branch delay slots. In general, no processor uses more than 1 branch delay slot, so they would have something else to deal with longer branch delays, and that's typically hardware branch prediction, which we'll talk about in our next discussion. So control hazards are introduced by instructions that change the control flow, explicitly through jump and branch instructions or implicitly by exceptions. You can flush and squash the wrong instructions in the pipeline. So for a jump or a taken branch, if you've already fetched an instruction sequentially that shouldn't be fetched, then that can be squashed. It just requires a little bit of modification to the existing hazard detection logic. We can make the conditional branch decisions earlier. That'll reduce the number of stall or squash cycles for branches. And we can use branch delay slots for short 1 cycle branches, delayed branches. So next time we'll talk about branch prediction, which is the predominant approach used in modern hardware to deal with control hazards caused by branch and jump structures.